Today we will move into another chapter or topic, new topic on compensator design using bot plot. This is actually the last topic in this course. Okay, this course, if you look into the syllabus, contain only 3 topics. Because we want you to also focus on design. I'm preparing assignment. So we hope that you will be able to do the assignment to improve the understanding on design, on controller design. We have done topic 2. Topic 2 is controller design, PID controller design using root lockers. Topic 3 related to frequency response. Controller design based on frequency response. This is the online, the chapter chapter outline. What will be covered in the in this topic or in this chapter. First, I will introduce you to frequency response. Mainly letter known as bot plot, how to plot frequency response, and also how to plot bot plot. Subsequently, the use of bot plot for stability analysis. This part was, I think maybe a few years back, maybe 2 years ago, it was in the previous course in 3133. But starting from that year, we moved this part into 3143. Here, the most important thing is bot plot. We will look into bot plot, then gain adjustment compensation. Remember in the previous topic, we also have gain adjustment control using root lockers. Here also we have gain adjustment. We have lag compensation, lead compensation. Remember in PID we have PI, we have PD. This is similar, lag and lead, and finally lag compensation. But we will not focus on this. Okay? We will only look into lead and lag separately. And later, we will also discuss or look into how can we design a compensator using MATLAB. Okay, let's start with the concept of frequency response. Usually, this is a common or a normal block diagram. We have a system, GS, and usually, previously we give step input to the system. If the system is stable, perhaps first order, second order, third order, or higher order, no problem. But if the system is stable, let's take this, it will go like this, maybe a bit oscillation, then stop. This is a second order system. This is input, step input, and this is output. We did this in the previous subject. But now what happens if the input is sinusoidal? if the input is sinusoidal and the system is a linear system, we have also non-linear system, but we will not cover non-linear system. If the input is sinusoidal and the system is a linear system, the output, we will see the output will also be sinusoidal. Okay. Sinusoidal input to a linear system generate sinusoidal response. So if you give input sinusoidal signal, output will also be the same pattern. And with the same frequency. If this is a frequency F, here also F frequency, same frequency. No change in the frequency. Then what are the differences? What the one that is changing in this case? However, they will differ in the amplitude. Okay, maybe here M, amplitude M in input. Output here is M naught, M output. They are different. And also in phase angle. We know phase angle. Phase angle like this. If we have something like this, and we use this to calculate phase angle, phi. So phase angle between these two will also be different. Again, if the input is sinusoidal, the output will also be sinusoidal with the same frequency, but they differ in the amplitude and also the phase angle. So that is the first basic concept of frequency response. Sinusoid in mathematics, we can also the signal can be written as M cos omega t plus phi. This is one of the techniques to represent a sinusoidal input, sinusoidal signal, where M here is the amplitude and phi is the phase angle. M amplitude, phi phase angle. This is one way to write, and it can also be written in a form we call phasor. I think you learned this in circuit theory, phasor. Phasor, we write in this form, M and angle phi. The M amplitude, phi is the phase angle. So we write M, symbol for angle, phi. This is another way to write to represent the sinusoidal signal. Using this, I will move to the next slide. Therefore, the system can also be represented by a complex number so that the product of input phasor and the system yield the phasor of the output. I will show here. Okay, let's say we have, I just redraw input and output. Input is M in, phi in. Okay, so it's a sinusoidal, amplitude M in, phi in is the phase angle shown here, okay, with the signal here. M in and phi in is the input. So here input. The output represented here, we know that the frequency is the same, but the amplitude and the phase is different. So we can also write here M, O, phi O. The lag give here, which is the system, usually we write GS in Laplace. In frequency domain, let imagine this is also M and phi. So if we represent the system by using M and phi by a phasor, we can obtain M naught. So the input M in, phi in, multiply with the system, M phi will give the output, M naught, phi naught. It's similar as GS multiply with the input. If we manipulate this, we know that if we multiply two phasor, it's equal to magnitude can be multiplied as usual. Mi multiply with M, and the phasor, the phase we add addition, phi in plus phi. That is the way to have a product between two phasors. The magnitude we multiply, the angle we add. Therefore, from here we can see that M naught, M output equal to here, to this, and the phase phi equal to the second term, the phase also. We say that the frequency is the same. When we apply input, sinusoidal input, the sinusoidal output will have the same frequency. Therefore, we usually use omega. Omega as the frequency. Omega is in radian per second. All in terms of omega. See, M in omega, phi in omega. Here also omega. All in terms of omega. So omega is fixed in this case. Finally, usually in frequency response, we will have omega. Okay, so here I put omega, omega all in terms of omega. That's why we call frequency response. Remember in previous case, we normally have in T, we have YT or CT or XT. That's why we call them time response. Here all in term of omega, in term of frequency. So we call them frequency response. Finally, we have what we call magnitude frequency response. Magnitude frequency response is this, M omega. And omega, if we can see from here, it's actually M naught, M output divided by M input. Okay, because we can equate M naught equal to M in multiply with M. Similarly, phi here is phi naught output minus phi in. That is called phase frequency response. So by now you should know that in frequency response we have two things, magnitude and also phase. Okay, the combination of these, we combine the combination of the magnitude and phase response, phase frequency response is called frequency response. So when we say frequency response, it contains magnitude and also phase frequency response. And usually we write M in terms of omega and also phi in terms of omega. This is the frequency response. And usually in frequency response, we will have to present in a graphical representation. Later, one of the technique is using dot plot to represent the frequency response of the system. Usually, we have a transfer function, Gs. The frequency response of the system, of a system with Gs, is obtained by we change Gs by substituting S with J omega. We substitute all S with J omega. And then and thus we will get G omega. Okay, so this is called frequency response. This is the transfer function. Normally, in frequency response, we show in this form, J omega. That is obtained by substituting S by J omega. As I mentioned just now, frequency response deal with many graphical representation. Therefore, we need to plot. Frequency response deal with many plots. And it can be plotted in many ways. These two are common ways to plot frequency response. First one is a function of frequency with separate magnitude and phase plot. So we have here two plots, one for magnitude, one for phase. They are plotted separately. For magnitude, we normally plot what we call, this is the magnitude versus omega. Omega is in radian per second. Magnitude here. This is one way to plot. And the magnitude is usually given in what we call in dB, in decibel. The magnitude will be in decibel. What is decibel? I think you use a lot decibel. I'm not sure. Maybe in when you learn filter design, use decibel. Maybe in communication also decibel. What decibel mean? Where this come from? Decibel. Okay. It's come actually from bell. There was still there. I think one of the famous lab in the US is Bell Laboratory. They propose a way to show ratio between two signals. If we have input, we have output, how can we show the ratio between these two? Okay. So they propose, let's say, V naught over V in. This is the way to just to show the ratio between two signals. Output over input. This is very appropriate to us later because remember that what we want to use, what we want to do here is to compare between output, sinusoidal output, and also input. That's why later we use this. V naught over V in is actually introduced by Bell Laboratory. That's why come decibel, Bell. Then people use log. V naught over V in. Why log? Because log, we use log to ensure that we can include a higher range of maybe frequency, a higher range of frequency, and also higher range of when we compare, if the comparison is too big, it's difficult to show in a graph, in the graph. So let's say here, if I want to plot a graph between 0.001, perhaps here 10,000, it is difficult to show in a graph. That's why they use log, because log 10,000 is 4. Log this one is also small, maybe log 0.001 is very small. It is between the range. Okay, -3. So we use log in order to include higher higher range. Okay, otherwise it will be difficult to plot. So that is where Bell come. Then deci. Deci is actually 10. Okay, decimal, decimeter, all 10. Deci refer to 10. So decibel is, then if we combine, become 10 log V naught over V in. And in power system, or in power, we normally have V squared. V squared over R equal to I. We have V squared. So then come, people try to use this. They square. But this is related to power. 10 log V naught over V in squared due to power V squared. Then if in log, we know that here can also be written as 20 log V naught over V in. this is one of the way to show the differences, to make comparison between two signals. And in the course here in control, we normally use this 20 log 2 signal. In this case, V0 over V in equal to decibel. And in more related one is M output over M input. Is equal to 20 log M is decibel. Okay, so the magnitude that will be presented in log in frequency response, especially in Bott plot later, is in decibel. That means we have to take 20 log M, which is M0 over M in. That is decibel. I return to this. So first, the magnitude curve must be between a graph of decibel, magnitude in decibel versus omega. And the other one is phase. Phase here in degree versus omega. Two separate graphs. That is for the first one. A function of frequency with separate magnitude and phase plot. Later, this is what people say as Bott plot. The Bott plot is a separate graph of magnitude versus omega and also phi versus omega. And the other way to represent or to plot frequency response is by using polar plot. Polar plot. Polar plot is the phasor length. It's actually M and phi. M is the length. Here they use length M. The magnitude represented by the length, and phi is the phasor. And they use the length to plot, not in decibel. Okay? It's actual M, actual magnitude. I will show one example later of the polar plot. That is for knowledge, because later we will focus more on Bott plot. Let's do one example on showing or plotting frequency response. Find the analytical expression for the magnitude frequency response. Here, one important term here which you should know is analytical expression. If you see previous, past year question, there were some questions asking about analytical expression for the magnitude and phase. So we have two, magnitude and phase frequency response for the system. Also plot the separate magnitude and phase diagram and polar plot. See, this is what first technique, and this is the second technique. And when we have GS, this is the transfer function. In frequency response, first we will have to transform into omega. It can be transformed by substituting S with J omega. Therefore, we substitute 1 over j omega plus 2. Once we have this, what we want is the magnitude. Okay, if we plot, if I make a plot here, xy, normal xy, this is maybe real, this is imaginary. 1. 1 here is 1 here. We can imagine as just 1. That means the magnitude also 1 from the origin. So 1 here is 1 over j omega plus 2 is something we can imagine as 2, maybe j omega here. This point, 2 plus j omega, or normally we call j omega plus 2. What is the magnitude? Magnitude is the length from here to that point. So we know the height here is omega. This is, so the magnitude is omega squared plus 2 squared plus 4. That is the magnitude of the system, magnitude frequency response. And again, as I mentioned just now, we normally want the magnitude in decibel. So in decibel, we use this formula, 20 log m. 20 log of this plus 4. We already have the magnitude. Next, we want the phase. The phase, again, let consider this plot here, the plot here. First, 1. One here, where it is here, is actually 0 degree. 0, the angle is calculated based on the standard x, positive x here. So 0 degree, 1 is 0 degree. In getting the angle or the phase, when we have 1 over j omega plus 2, we normally take angle at the numerator minus denominator, minus. It is phasor, is in phasor. If we divide, then we minus. 0 minus this angle. Angle here is here. Theta. We know omega, we know 2 here is actually tangent, inverse tangent omega over 2. Tangent, inverse omega over 2. So that is the phase frequency response. We need magnitude, we need phase in order to plot the frequency response. Any question here? Any question? until now? Okay, let's move. So we have, I will rewrite the magnitude and also the phase. Magnitude is 20 log 1 over omega squared plus 4. And the phase is minus tangent inverse omega over 2. Omega over 2, yeah. Okay, now let together, I want you to do also. We want to calculate some data and complete this table. Omega in radian per second. We want Gj omega. Gj omega is the one without not dB. Not dB mean only this one, 1 over omega squared plus 4 without dB. Next one, I want in dB. So I use here dB. And then we want this, the phase. Let's try 0.1 radian per second. 1, 5, 10, 100. They are all now calculate Gj omega here. Substitute 0.1 into here, Gj omega. And then once you obtain that, get the one in dB. What is the value here? 0.1, the magnitude. Anyone?
The 0.5 Doctor.
0.5, right? dB, 20 log 0.5.
Negative 6.03.
Negative 6.03 dB. Okay, I want apa ni? Phase. Tangent inverse 0.1 over 2. Tangent inverse negative 0.1 over 2.
Negative 2.86.
86. Okay. This all this is degree, yeah. All degree. Okay, let's move to 1. So now 1 over square root 5. Maybe also near 0.5. 1 over square root 5, 0.45.
0.45.
Okay. dB, 20 log 0.45. In dB,
Negative 6.99.
6.98. 99, yeah. Here minus tangent inverse 1, half, 0.5.
Negative 26.57.
57 degrees. Okay.
Yes.
Okay. Let's do all. This one you skip 5. Later you complete 5. 10. If you continue, you get 0.098. Here, this is minus 20 dB, minus 78.7 degrees. 100. 0.0099. Here minus 40, minus 88.8 degrees. Yeah, I want you later to redo so that you make sure you get about the same. This is the table in which we can use the data to plot a graph. Okay, this is the graph. The graph here I took from the textbook. I extract from the textbook. Before that, I may forgot just now. Okay, the one that we will draw here is dB, the magnitude in dB, and also phase in degree versus omega. Then this is omega, omega. And the one that we will plot is using what we call semi-log. Why it is called semi-log here? Why this graph is called semi-log? Anyone can help? Why this graph is called semi-log? This graph is called semi-log. Semi mean half. Because y-axis here is not log. The value log, but the scale here is not log, it's normal. 6, 12, 18, 24 in dB. But in dB, to get dB, we have to log. That is different thing. But the scale here is common, normal one. You see scale in the x-axis is log scale. Okay. Semi-log refer to because x-axis is in the scale is log, y-axis is a normal scale. So half log. Why we want to use log on the x-axis? Again, because we want to have a wide range of frequency. Okay, you see here, by using log, we can use 0.1, we can use 100 in a graph, in one graph. If we use a normal graph, normal scale, how can we have 0.1 and then 100 or 1,000? In fact, you can go to 10,000. So the graph will be, we cannot cover a wide range. So 0.1, 0.2, 0.3, how can we get 1,000, 100 or 1,000 in one graph? So we use log. So log here to cover a wide range of frequency. Okay, you know frequency normally in what 10 kilohertz, 100 kilohertz, sometimes 0.1 hertz. So we want to see the response within a wide range of frequency. That's why in X we use log. And we have to use what we call a semi-log graph. A semi-log graph here have normally if we have a face-to-face lecture, normally I will bring a graph so that you can see the graph to understand how it works. So a graph here, a semi-log graph, a log scale here for x. If you see the graph, there is no zero. There's no log zero. Log something, there is no log, you get the value of zero. Okay? Must be 0.01, 0.11, no zero. So the graph has no zero. You can start with, let's say, 0.1. If you choose this one, 0.1. The scale you see start bigger, it start big, but reducing the scale. And up to here, we use 1. We take as 1. And next one is 10. The other one, 100. The other one, 1,000. From here to here, we call decade. So here in this graph, there are 3 decades. One, here another one, another one. Normally, a normal graph paper have 5 decades. So if you start 0.1, 1, 10, 100, 1,000, 10,000. Normally, a normal graph has 5 decades. Okay, so that is the introduction information on the graph here. That is very useful because board plot will be using this one. Let's look into our result here. When 0.1, magnitude -6, phase 2.86. So we can see here 0.1. 0.1 here is here. The output is here. It cannot be seen here. It's -6. The graph is like this. -6. And phase -2.86 here. -2. Okay. When at 1 radian per second, 0.45, minus 6.98, almost 7. 1 radian per second here, you can see here is actually about 7 dB. And the degree, the phase is -26. 1 here. Okay, you can see here about -26 here, -26 degree. Okay. Next, we look into 10, -20 dB. 10. This is 10. Okay, here -20. Between 18 and 24, here -20. And the phase is -78. 10 here. Here -78 almost. And finally 100 -40. 100 here. Here 100 -40. And also the phase is -88 or 89. Okay, nearly 90. This is the first technique to plot, which is a separate plot between magnitude and phase versus log omega. And of course, to get an accurate one, we need all points. Okay, before that, to read here, this is 0.1, here 0.2, 0.3, to 1. Then 1, 2, 3, 4, and 10. After 10, become 20, 30, and so on, up to 100. So in order to get an accurate one, we need to, of course, we need to calculate every point. The one that we calculated here is just the point at 0.1, 1, 10, 1,000, 100, and so on. Similar to here, if we need a more accurate one, then we need to have more data. I think this is plotted using a computer, using MATLAB. This is one way to plot, and later, as I mentioned, this is called board plot. And we will have more detail on board plot later. The second technique, as I mentioned here, is polar plot. Polar plot, in contrast to this, polar plot try to combine magnitude and phase into one plot. And this is the example of polar plot. This is a polar plot. How it works? Yeah, this is real exists, RE real. Here imaginary exists. And we see, let's say we take one data, 0.1. Polar plot is not in dB. They use a normal one without dB, 0.5, and angle minus 2.86. How to plot how to have polar plot? We take just now minus 2.86 degree and magnitude 0.5. From here we take minus, if I we take minus 2.86, let's say this is minus 2.86 degree, minus below real axis become minus, and the magnitude here is 0.5. The magnitude means the length. So they get this point. This point is angle minus 2.86, length 0.5, and they write at the point 0.1 radian per second. This is how they get this is how to get the point in polar plot. Similarly, we have 1 radian per second, 0.45, 26. 1 radian per second minus 26 degree, 0.45. Okay, 26 here. This is radian. 26 degree. Here, 1 radian here. And here 26 degree, and the length is 0.45 length. They get this point. Here, many points were taken, 0.2, 0.3, and so on. Then also, if we see here at 10 minus 0.08, 78. Then here, this point, the angle 78 degree minus, and the length is 0.098. 0.098. Length 0.098. So get all the data and then plot. This is called polar plot. This is for your information. It will not be asked in the exam because we will focus more on the plot frequency response. Again, to inform you so that you know there is another plot that combine frequency, that combine magnitude and also phase in one plot. Okay, we'll take about 10-minute break. Then we will continue with another example on finding or plotting the frequency response. Let's continue with this example. Find the analytical expression for the magnitude and phase frequency response for the system here. GS 3/S plus 1, S plus 5. This is similar to the one that we did just now, which is 1/S plus 5 or S plus 2. Okay, this is here we have two poles, S plus 1, S plus 5. Plot the separate magnitude and phase diagram. Okay, when the question want analytical expression, that means we want the formula G omega equal to what? Okay, again, it can be obtained by substituting all with substituting S with J omega. So here J omega plus 1, J omega plus 5. Magnitude is 3. Again, if you want, you can like make coordinate here is 3 here. 3, that means it's 3. Magnitude 3 here. When we have many poles like this, we can do it one by one separately. For this one is J omega. You can imagine 1 J omega here is here. So the magnitude is omega squared plus 1. And the other one we can do, you can, if you want, you can also open the bracket here. You can multiply together, but maybe easier you can you do one by one. Omega squared plus 25. Okay, 5 squared. So this is called expression, magnitude frequency response. So this is the analytical expression of the magnitude frequency response. And of course, finally, we also want in dB. You can multiply with the 20 log. dB is 20 log 3 over this. That is the expression for the magnitude. Okay, now let's see phase, for the phase. Okay, G omega equal to 3 phase 0, because on the real axis 0. Again, when we have denominator, we have to minus. Okay, in angle, if we divide, that means we minus. Minus, also one by one, tangent inverse omega over 1, that means omega, plus tangent inverse 5 omega over 5. I add here and then 0 minus all together. Omega over 1, omega over 5. So this is the expression. Again, expression for the phase. Expression for the phase. Once we have this, we can also again make a table. Omega, the magnitude in dB, and also the angle. You have to decide the range of omega. Normally in the exam, they will give the range of omega to be taken, maybe 0.1, 1, 5, 10, 1,100, and so on. Okay. Once we did, later we will go into detail on dot plot. Then at that time you will you can estimate. You will know how to estimate the range of omega to be considered. Okay. So I would like you to do this to find G and magnitude in dB and also the phase. Please do it based on the expression that we have derived. And this is the output. I plotted using MATLAB and paste it here. I will send this one to the group so that you can compare the result that the data that you get, that you calculated and put in the table. You can compare with this. Okay. Bot plot, they have they can plot here up to 4 decades. You see, this is 1 decade, another decade, this is another decade, 4 decades. At start here, it is automatically determined. I mean, the scale is here 0.0, 0.01, 0.1, 1, 10, 100. Okay. So you can check when you calculate for 1, what is the value of phase, and also the magnitude here in dB. This is for 10 radian per second. 0.1 is here. And just to inform you, in MATLAB, you can first define the numerator 3. You can define the denominator, in this case 1 and 5. Then in order to plot, there is a command called BOT. Numerator and denominator. You input this one, then you get dot plot. The dot plot is a separate plot between magnitude and phase, both versus omega, radian per second, omega in radian per second, and the omega is given in log scale. Okay, please do this, and later I can send you. I can give this one also. I just added into the slide. And you can also compare if you invoke into MATLAB, if you run MATLAB. Let's start, let's go more detail on dot plot. The log magnitude mean dB here, and phase frequency response curve as a function of log omega is called dot plot. So a separate magnitude versus log omega, and also phase versus log omega. It's called dot plot. Dot plot is one technique for analysis and design of control system. Similar to the time response, similar to the root locus, in which you can analyze the system, you know whether the system is stable or not, and that then we can use to design PID. Dot plot is the same. Dot plot can be used for analysis. We know whether the system is stable or not from dot plot. We know how strong is the stability. Then we can also use dot plot to design a controller to achieve desired response. That also in overshoot, in settling time, rise time, error, can also be done by using dot plot. If we have a transfer function, consider a transfer function in which S equal to K, a constant, S plus Z, 0, 1, 0, 2, and so on, divide by pole, the denominator, pole 1, pole 2, pole 3, and so on. We can, this is the transfer function, then we can, of course, transform this into j omega by substituting S into with j omega. So all will be K, j omega plus Z1, j omega plus Z2, and so on, divided by j omega plus P1, P2, P3, and so on. And that is called frequency response. Then we can, of course, obtain the magnitude. Okay, magnitude is obtained by, we can do one by one. J omega plus Z1, we get this magnitude. Then we get magnitude for j omega plus Z2. Similarly for j omega plus P1, P2, P3. Okay, continue. That one for the magnitude frequency response. As we want them in dB, we have to take log. Then we have j omega in dB is obtained by taking 20 log this one. 20 log of this. In log, we know that when we manipulate log, if we have log AB is equal to if this is multiplied, then we can just in log we can add log A plus log B. If we if these two, if A divided by B we log, then we minus log A minus log B. Okay, if log A B over C, then A plus B minus C. Log A plus log B minus log C. That is log. And we want to apply the concept here. When we take log, 20 log of this, so here K, we can 20 log K, we can add with this one, we can add because we multiply. And at the bottom, we need to, we can minus, we can subtract because they are, because we divide. So it will be 20 log K plus 20 log J omega plus Z1 plus all for 0 minus 20 log J omega plus P1 minus 20 log J omega plus P2 minus all 4. So it will be 20 log K constant plus all for the 4 for the 0 minus 20 log all for the 4. This can be done. This is true because we use log. So this is another way, another advantage of using log, because we can, instead of multiplication and division, we can add. We can do addition and subtraction in log. Later you will see that this is useful in plotting dot plot. Then we also need to find the phase frequency response, G omega is equal to, this is already, we take phase of this, and we know that phase angle, when we multiply, we can add the angle. When we divide, we minus the angle. So it will be angle of K plus angle of J omega plus 0, 1. And then 0 for 0, number 2, so on, minus J omega plus P1 and then J omega plus P2 and so on. Minus all 4. Because the magnitude is addition and subtraction of each constant, pole, and 0. And also the phase frequency response is also addition and subtraction of pole and 0, and also for K gain for the constant. Then if we know the magnitude and frequency response and phase response of each term, if we are able to find for each one by one, then we can get the total response by algebraic sum of each term. I mentioned this is one advantage. If we can get one by one separately, we can get for K, for 0, 1, 0, 2, pole 1, pole 2, and so on. Then we can just do a simple addition and subtraction in order to get the total magnitude. Similarly, we can do addition and subtraction for the phase in order to get the total phase response. So this is the way used to plot to sketch bot plot. In bot plot, we have to do one by one, each for each term. Finally, we add together. The frequency response can be okay, this one first. Therefore, the total response can be obtained by graphic addition. We can add one by one. And in bot plot, we will use what we call straight line approximation. Remember the table in which we omega G, the gain in dB, the phase. In order to plot, we need to obtain many data here. Many data of W, which we will not be able to do. We will not be able to draw like this. This is MATLAB, computer drawing. It's okay, computer can obtain many data and draw an accurate one. We will not able to do that. We will do what we call approximation. And it is called straight line approximation. Straight line approximation. We want to draw bot plot, but later after this we will not use the table. We will not taking data one by one. We will do what we call approximation. It will be faster, will be easier as compared to, of course, by calculating one by one. Because the one that I show here is a simple one, 3s plus 1, s plus 5. What happens if we have many? Then calculation will be more complicated. That's why we need an approximation. It's like a sketching. In root local, we call sketching. Here, we call approximation. Straight line approximation. I will stop here. In the next class, we will move. Tomorrow, we will look into straight line approximation. How can we plot bot plot? How can we sketch bot plot using straight line approximation? I will stop here. Any question? Before we end, any question?